Think about this for a second. Right now, there are literally millions of miles of pipes transporting highly pressurized steam, volatile chemicals, and crucial energy resources across entire continents. It's an absolutely staggering feat of engineering. But what keeps it all from just bursting apart? Well, welcome to This Explainer. Today, we are uncovering the invisible shield of rules that keeps this massive global infrastructure totally reliable and, more importantly, safe. Okay, let's dive right into this using a funnel approach. Here is what we're covering today. First, decoding codes and standards. Second, the evolution of piping rules. Third, ASME, the master codes. Fourth, ASTM and API explained. And finally, number 5, the global safety standard. All right, let's kick things off with Section 1, decoding codes and standards. Now, before we really get into the nuts and bolts of the infrastructure, we have to clear up a massive misconception in the industry. While every single country technically has its own specific set of regulations, American national standards are universally accepted globally. Seriously, whether you're building a state-of-the-art refinery in the Middle East or a massive power plant in Asia, compliance with these American requirements is the standard for piping design and material selection. They are the true global baseline. Now, you're going to hear the words code and standard thrown around together a lot. People often say them like they're the exact same thing, but they're really not. A code dictates high-level requirements. It tells you what you need to do. It sets the overarching rules for design, fabrication, erection, and testing. A standard, on the flip side, tells you exactly how to do it. It contains the highly specific design and construction rules for individual pipe components, the materials, and the equipment. And this brilliantly illustrates the difference. Let's think about a simple fire alarm. A code is the big rule that says a building absolutely must have a fire alarm system installed before anyone can legally occupy it. It's the high-level mandate, right? The standard, though, is the document that spells out exactly what kind of fire alarm system it needs to be, exactly how loud the siren must be, and exactly how the wiring must work. So remember, the code is the mandate, and the standard is the manual. This distinction totally applies to how compliance is enforced, too. Adhering to a code is generally mandated by law. You'll have regulatory and enforcement agencies breathing down your neck to make sure you follow the code. Compliance with a standard, however, is normally required either by the purchaser's specific contract requirements or because that big, overarching code specifically references the standard, which essentially pulls it into the legal requirement. Just to round out our definitions here, you might also see something called recommended practices. Now, unlike rigid codes and standards, recommended practices are completely optional. They're basically documents put together by professional groups to indicate good engineering practices. They're highly respected advice for sure, but they aren't the law. Moving right along to Section 2, the evolution of piping rules. You know, these rules weren't just drummed up overnight in a boardroom. They are the result of hard-earned lessons over decades. Back at the beginning of the 20th century, as industrialization was just absolutely booming, things were getting dangerous fast. So in March 1926, a project began to develop the overarching B31 piping code. By 1942, it evolved into a single comprehensive standard. But here is where it gets really fascinating. By 1955, the industry had become so complex that they realized, hey, we need to split this code up into specialized industry-specific documents. And that directly led to the publication of the famous Petroleum Refinery Piping Code, ASA B31.3 in 1959. We've seen how they evolved, but it definitely begs the question, who are the people actually sitting down today and writing these incredibly complex, globally enforced rules? Let's meet the master architects. That brings us to Section 3, ASME, the master codes. So, the American Society of Mechanical Engineers, or ASME for short, is the primary governing body responsible for those overarching design codes. They dictate the what of our global infrastructure. They manage the entire B31 series, essentially chunking the industrial world into highly specific categories. You've got B31.1, which handles the massive steam pressures in electric power generating stations. Then there's B31.4 for transporting crude oil and liquids across vast distances, B31.8 for gas transmission, and B31.9 for the complex building services piping hidden inside high-rises and commercial buildings. But this system isn't just static. It's a living, breathing set of rules that constantly adapts to reality. Over the years, ASME realized some of their codes were just redundant. For instance, B31.6 for chemical plants and B31.10 for cryogenic piping, they were never even officially published as separate standalone documents. Why? Well, because their requirements overlapped so heavily with other codes that ASME simply merged them into a broader code to avoid all the confusion. So the absolutely crucial point here is that because of all those mergers, ASME B31.3 emerged as the absolute heavyweight champion of the entire industry. It's known as the process piping code. If you're an engineer working in petroleum refineries, chemical plants, pharmaceuticals, textiles, or even semiconductor manufacturing, B31.3 is your Bible. It covers everything from raw chemicals to steam, air, and cryogenic fluids. Without a doubt, it is the most important code for process piping professionals globally. Now, ASME also handles the equipment that generates all that pressure, because while piping transports the pressure, the vessels actually hold it. To handle this, ASME has an 11-section boiler and pressure vessel code, often called the BPBC. Out of all 11 sections, Section 8 is the one specifically dedicated to the rules for pressure vessels. It's an absolutely essential companion piece to the piping codes for any process engineer. Okay, let's look at the other side of the coin. In Section 4, ASTM and API explained. So, if ASME gives us the overarching codes, the what, we now need to understand the how. These are the specific standards for materials and specialized equipment. First up is ASTM, the American Society for Testing and Materials. They are a technical organization that publishes voluntary standards completely focused on what materials are actually made of and how they perform. They set the highly rigorous test procedures for verifying things like a metal's exact chemical composition, its tensile strength, and its bending properties. And these ASTM standards are massively comprehensive. They cover refined materials like steel, and they are meticulously organized into 15 distinct sections with various volumes. But what is truly fascinating here is the legal transition. While ASTM standards start out as voluntary, the exact moment an overarching ASME piping code says, hey, you must use steel that meets ASTM specifications, that voluntary standard instantly becomes legally mandatory. That's exactly how the code gives the standard its teeth. Then we have API, the American Petroleum Institute. While ASTM tests the raw materials themselves, API is intensely focused on the final product for a specific industry. They publish specifications and standards designed specifically to aid in the procurement of standardized, safe equipment for the petroleum, petrochemical, and natural gas industries. Take a look at how insanely targeted these API standards are compared to the broad ASME codes. Let's say you need a pressure-relieving device in a refinery. You go straight to API RP520. Buying a centrifugal pump, you ensure it meets API 610. Building a massive welded oil tank, API 650 is your exact instruction manual. It basically allows purchasers and manufacturers to speak the exact same highly technical language when ordering critical equipment. Finally, let's tie it all together in Section 5, the Global Safety Standard. Now, what's really interesting about this is how all of these disparate acronyms actually build our world. They form a complete working ecosystem. We've talked deeply about ASTM, ASME, and API, but they also combine with organizations like NACE, which focuses heavily on corrosion, and AWS, the American Welding Society. They don't compete with each other, they collaborate. They create a beautifully unified engineering language that governs everything from the raw ore mined from the earth to the final weld on a high-pressure gas line. To sum it all up, this cohesive system is exactly what keeps our modern world running safely. Codes, like ASME, act as the structural law, dictating the overarching design and safety mandates. Standards, like ASTM and API, provide the exact recipes for the materials and equipment needed to fulfill that law. Together, this incredibly tight handshake between what to do and how to do it ensures that a facility built in one hemisphere operates with the exact same mathematical certainty of safety as one built in another. It's an amazing global achievement. But you know, the world of energy is never standing still. With the massive global push toward new highly volatile energy sources, ASME has already had to publish B31.12 specifically for hydrogen piping and pipelines, which leaves us with a pretty provocative question. As our technology pushes the absolute boundaries of physics, how will this invisible shield of rules evolve next to protect the infrastructure of our future? It's an incredible engineering puzzle and one we will for sure be watching closely. Thanks so much for joining me for this explainer, and keep learning.